All right, you guys, this is going to be the second PowerPoint for this week. And when we talk about materials that electricity is used to control and move through, we break it down into three of these. Okay, now what you're going to be doing is filling in that chart in the Cornell Notes. You notice it's got three columns and we got two lines. So those are your top lines. You got your conductors, your semiconductors, and your insulators. So another way of looking at it in kind of a silly, goofy way, that's just me, is conductors really like electricity and they allow it to go through. But semiconductors, they're kind of, some, 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 right? Okay. Insulators, no, they do not let stuff go through it at all, at all. So in your bottom line of boxes, you're going to have conductors allow electrical flow. In your middle bottom box, you're going to have some electrical flow or allows some electrical flow, and then insulators prevent, or however you want to say it. You're just filling in those boxes. But that right there lets you fill in your chart on your Cornell Notes. Okay, so what do we make semiconductors out of? Okay, they show up all the time, and you don't know them, with the level of information we have right now. You don't know them when you see them, but they're made out of silicone and germanium. And actually, if you've ever looked at a computer motherboard, if you've ever had your motherboard on your computer die, it's a horrible experience, believe me. Those circuit boards, all those little rectangular chips, computer chips, it's a semiconductor. It lets some electricity go through, but not all of it that came in. That's why your computer, your desktop computer, has to have a fan, because those things get pretty hot, like the computer that's usually sitting on the teacher's desk. And if you notice on a laptop, if you have it on your lap, you'll notice it gets warm. It's taking electrical energy and converting it into heat. But it's integrated circuit boards, it's the motherboards, it's your cell phones, remotes. If you've ever looked up anything electronic, you've seen semiconductors, and that's what they look like right there. All right, so let's keep moving in. With that, we got semiconductors, what are they made out of? Those two materials, and you may recall that those are materials that are on the periodic table. They get along with electricity very well, and if we were looking at our table, we could actually figure that out and say, oh, okay, look at the chemical properties, blah, 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 right? Okay, so let's keep moving forward, okay? And some examples of semiconductors is our pretty bright, brilliant one called the diode, light emitting diode. The key thing about a diode is it lets electricity go in one direction, but it doesn't let it go and then come back. Alternating current that's used in your house utilizes alternating current. The electrons go into something and then they go right back out. And there's a constant movement of that. It has a certain frequency to it. But diodes convert it into direct current, DC, like your automobiles use. Okay, the cool thing about those, and I'll show you some pictures of them here. We've got light emitting diodes. Those were actually invented in the 1960s. But little components like that you see on circuit boards, they're diodes, and the striping gives you information about the amount of energy that thing can use or absorb. Okay, the advantages is they're small and they fit, on a circuit board. You can design them well, and I've designed with them. It's been many years. And you say, oh, I need this diode here, I need that diode there. And as long as you don't fry them, they last forever. And so they use a lot of these in traffic signals, and they usually don't get that hot. So you don't waste a lot of electricity. The other thing is the transistor. Now, a transistor used to look a lot different. Like in the 50s and 60s, a transistor radio had these glass tubes in it. Not anymore. We found stuff to make them these days. This is a very common device that is a transistor, but we call it a relay. Where in the world do you run across a relay? The turn signal in your car. And how a relay works is if you were to hold up both hands in the air, and let's say the contact is your left hand, okay? And then you've got this little switch that's going to go back and forth. In other words, it's going to swing over and touch your left hand. Okay, your right hand is at a certain point is going to come over and touch your left hand. Okay, but we got to pull it back because we haven't energized the relay yet. When an electrical signal, like from a switch, comes into a relay, it causes the switch on the inside to come over and hit the contact. And what you do in that is you are changing the course of electricity. Instead of it going to that circuit, it's going over to that one. So if you can imagine, oh boy, like a set of stage lights, something like that, that you want on to be at a certain time, but you throw one switch and all the power goes off to one set of lights and it comes on for another set of lights. That's how a relay works. And I just showed you a real simple diagram here, how you wire it up. This is really a good example for the car. You have to have something with constant battery power to it, constant. But then look at number 85, I think it is, key on. Oh, no, wait a minute. If the car's just sitting in the driveway and you're in the house, the key is not on. So when you turn the key on, that's when it switches over and provides power to this other thing. Like I said, turn signals. Every time you turn on a turn signal, you hear that bink, 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 you know, that clicking sound. It's a relay. It's a relay that's been designed to come over and slap the contact at a certain interval, a certain amount of time. So that's how a transistor works. Now, I wanted to show you this too. When we're trying to understand the concept of electricity, there's tons of videos out there that you can see. But let me kind of paint it this way. I would do this if we were in class. Think of a river, okay? I got the picture over there on the left. Very calm river, we're just going down it. Lots of water, right? Look at the picture on the right. Same amount of water at any given moment, but what's the difference? The speed that it's moving, the current. That's why you always see and read and hear people say, it's not the voltage that'll kill you, it's the current. A 2 amp current in your car, the electricity is moving much more slowly than a 30 amp. Here's what I mean. Okay, it's a lot like a river. A river has a current, so does electricity. It creates a force when it moves. It has volume, okay? It has an amount, and it has things that it moves against. Resistance, that's where the resistance is. In a river, it's like sand, rocks, land, dirt, you know, crap, trees, okay? So look at this phrase in the middle here. It's not the amount of water that will kill you, it's the current. Now, the picture on the left, could you stand in that, you know, that river and be okay? Yeah, so the amount isn't the issue. The voltage isn't really the issue. The issue is the current, okay? So let's break down some electrical terms here real quick, and I'm going to help you define what they are. The volume, just like a river, the volume of electricity is measured in volts. How much water are you talking about? Are you talking about a stream, or are you talking about a great big river? Okay, that's the volts. The current, the amps, is how fast it's moving. Okay, and just like with the two pictures, we got water that's nice to stand in and water that's not so nice to stand in. Okay, we could say that the picture on the right has more amps than the one on the left. Okay, and the amount of resistance that we can also measure is measured in ohms. I could have 2 ohms of resistance. I could have 30 ohms of resistance. Now these are all very related, and next week we're going to play with mathematically how they're all related. And this is a very big long PowerPoint. Sorry about that, but I wanted to really drive these points home. Y'all have a good weekend, and don't forget to upload a picture of these completed notes for this week. Okay, y'all take care.